Hi guys, today we're going to do electrochemistry. Electrochemistry for A2. Now we won't do the electrolysis first. We'll be doing standard electropotentials first. We go backwards. So a few terms you need to be clarified. So here it says standard, right? Electropotential. Now the standard is same as this one here. Okay, this is a sign for standard. So electrode, which means there must be a metal, there must be a conductor. Potential means a difference in energy level. Here, of course, difference in electron potentials, right? So standard potentials and standard cell potentials are two different things in this equation. So there are three important things that we ask you. One, of course, is on standard potential. One is called standard electric potential and standard cell potential. The difference is electrode and cell. Last one is Nernst equation, okay? So there is also in the question, it says define, that means what it does mean. So there's a difference, a slight difference between standard electrode potential or redox potential and standard cell potential. We will look at this later after we discuss all these things here, okay? Right, today we will try to do A, B, C. Hopefully we can finish on time, all right? It's, let me just put down the timer first, otherwise I don't want to shoot all time. Okay, now to understand these things here, I'm going to use a few things here. Now, see, according to theory, when the piece of metal is immersed in a solution of water or is aqueous ions, right, it will form an electric double layer. Now, it's like you would form one, form two. I don't know, you throw a piece of metal, for example, a very regular metal, and sodium into water atmosphere. It will dance it, and then you will change, So you put a piece of sodium, right, and a metal into water, right, water. What happens is the sodium will be very reactive and become what? Na positive, isn't it, right? Give electrons. Of course, these electrons will be taken by hydrogen, H plus. Let's put that, okay, to become H2 half gas. Okay, pop, come out, it will burn, isn't it? So remember that metals can become ions when you put in the water. So there's a possibility of that happening. So what happens is, I'm going to show you here, right? Now this is the metal layer, okay? This metal here. I'm going to show you another diagram, which is probably better, okay? Like here. Now this is a metal layer, can be sodium, whatever. Okay, now let's take let's say it's sodium. So now this water. Instead of solution, put water, H2O. So when you put inside here, there is a motive, the force causing it to come out. So here, all here is the metal atoms. Is in, and very, very big, of course, it's nano size. Okay, it's a sodium. Imagine that. Okay, this is your sodium here. Okay, and of course, it's sodium packed. Why? Because they are close packed now. Okay, don't care. Na, what is Na and Na here? So once you water here, it can come out. There's a force because of reactivity, okay? So as it come out, what happens there? Let's say pieces of the tools coming out, okay? And as it comes out, here is your Na plus, okay? And here they work as your ions, and left behind one electron here, okay? So they form an Na plus and so forth, Na plus, and lots of ions are formed. I just put a plus, okay? Blah, 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 a plus, plus, plus here. And you form what you call a double electric layer. So there is going to create, right, on the surface of this metal here, all along here, right, two layers, okay? They call it a double electric layer, right? So it says here, first, like here, first stage of formation of double electric layer. So there's a possibility, and on the surface of the metal, this metal here, there's a lot of electrons. Okay, so so there's a difference in potential, okay, between the solution now and the metal, right? So this is called potential, electric potential. Okay, so the difference. So can you measure the potential? Obviously, there's no way to put electrodes into here and measure potential. So what they did was they need to have a comparison of two such cells and see who will have a greater electron density. This is called greater electric or electron density on the surface. That means it will have a high, if it's a greater, that means a high potential. Now, let's just let me take you here, okay, to two metals. Okay, a straight jump inside here. Now, actually, if you want to go, maybe I go to there. Okay. Now, if it's zinc, now this is the thermochemistry part of it. Okay. Now, for zinc to become Zn2 plus aqueous is here. Now, this is the whole equation here. Okay. So zinc has to first become gas, right? This is your heat of what? Heat of what? Atomization. Yeah. Yeah. Right. From here to here. 1 mole of gaseous atoms from its elements, standard state under standard conditions. Okay, gaseous. So from gas to here is of course the first. So this is the value. This is your delta H of atomization. This of course is your first and second IE is not first plus second IE. Okay, where the gas you remove 2 electrons. And of course here's your heat of hydration. Of the ions, remember, we just finished, right, of the ions of zinc 2 plus. So all this heat give out is delta H positive. So thermodynamically, positive means not feasible, but of course this can be easily feasible if there's enough heat in the water. So zinc will slowly dissolve. Of course, with sodium, it'll be negative, like it'll be very negative. Right? With sodium is very negative, right? So it's very active. So zinc will take time, because it will absorb this energy from the what? From the solution. So we form a double electric layer. The layer is between the zinc 2 plus and the electron that's left behind in where? In the electrode, in the surface of the zinc metal. Okay, so we have a double electric layer. The potential between the surface of the metal and the solution. Okay, now this is the electrode potential. So what this value here, whatever is it, we call it E, okay? Depends on what? Well, depends on 2 things. The type of metal. But sodium will have a high potential. And secondly, if I were to put, if I will put here zinc in water, H2O, pure water, and I put zinc in a solution of zinc 2 plus. Normally, as I said afterwards, the standard here refers to the zinc 2 plus in this water is 1 mole per dm cube. Okay, molar. So of course, in this case here, if you put the equation Zn solid plus AQ reversible, Zn2 plus aqueous plus 2 electrons. If it's reversible, of course, in the first case here, more will come out, okay, right? Because this one is 0 here. But in this case here, because it's a high concentration here, it will not come out so much. That means the surface here, let's say we have 100 electrons. Here we only have 50 only, because the Zn2 plus will force it to go backwards. So the potential will depend on the type of metal, like zinc or copper or sodium, and also the concentration of the solution. These 2 things will control it. So now that's the idea first, okay? So now, so how do we compare this with, to get the, we call it electrode potential. How do we measure it? Whole thing is to compare with something, okay? Compare with another thing which is standard. Okay. So here we use hydrogen. Okay, now this is called hydrogen electrode. We will take it as 0, no, of course not 0. Okay, now let's say, let me explain a bit. Okay, now here is a hydrogen electrode. So now this is like DAP, it's a rocket here. Okay, and inside this tube here, right, is all, it's not air, no air here. Okay, make that, make no mistake. Okay, no air here. So if now this contraption here is a tube. If I want to put hydrogen here, it means all of the hydrogen. I put chlorine here, all of it chlorine here, right? So I put here hydrogen. Hydrogen is my test. It's my test or my standard H2 gas. And for this to be standard, it must have temperature equals to again 25. Remember, this is the same value you give for a standard temperature for your thermochemistry, okay? Not for gas laws, okay? Gas laws standard means 0 degrees centigrade. That will become ice really cannot. Pressure, again, is 1 atmosphere, okay? Like normal pressure, right? And this here, you fill all with hydrogen gas, right? So to make it standard, of course, I make here a solution of 1 molar of H plus. Can be 1 molar of HCl or 0.5 molar of H2SO4. This is the normal one used, okay? Because nitric acid can be quite a problem because NO3 minus can be an oxidizing agent, so we don't use that one, right? So these two are being used. Now, so I put the wires here, and here is an electrode. It's a platinum. Why platinum is used as standard because unreactive. It got platinized. Platinized means let's say now this is a flat piece of metal, okay? Pure shiny platinum. The surface is very smooth, but so smooth that it's not very, not very activated. So what they do is they coat it. They undergo anodization, and the surface here is like this, okay, coated with platinum. So a lot of surface area there. Okay. So it's called platinized, okay, right? Platinized, okay. So the as you pass hydrogen gas here, the hydrogen gas can be trapped inside here, plenty, okay, inside here. Okay, so platinized, but don't worry, normally just put platinum electrode. So because it's stable, can use gold, yeah. Normally carbon is not used, okay, because platinum is more reactive, okay, more more sustainable, things like that. Right? So as you pass hydrogen inside here, you pressure it, see it's pressure higher than here, so it will dissolve inside here. So inside here there's a lot of hydrogen gas, okay, and a lot of H plus gas. Okay, so inside here that means there is going to be a potential. Remember, if it's zinc, like zinc here, right? Okay, if it's zinc here, I put here, no, here, right? So if it's zinc here, there'll be a layer of Zn here. Okay, and let's say here. All right, maybe I'll put it here. Okay, hydrogen here. Okay, so as hydrogen here, right? So hydrogen gas can become, right? As it stick onto here, hydrogen also can undergo ionization, you see? Okay, becomes 2H plus equals plus 2 electrons. Okay, but the H plus here will cause it to go backwards. So there also exists in this case here inside this platinized electrode here. Okay, there's H plus here. H plus, they form a double electrode layer. H plus all along here. The H plus coming from here and H plus coming from here. So they're all plus. Okay, and he got electrons. Electrons come from where? Hydrogen that is ionized to here. Okay, hydrogen again can ionize, don't think cannot ionize. But of course, the rate, right, is not as fast, as strong as sodium now. Okay, so okay. Now let's say the hydrogen in this standard condition at 1 molar H plus in the solution is 1 molar. Okay, 1.00 mole per dm cube. And of course, the temperature is equal to 25 degrees centigrade. Okay, and the pressure equals to 1 atmosphere. Let's say the number of electrons on this surface here is 50. Okay, 50,000. Let's say 50 electrons, okay, to make it easier for us. So there's a potential of 50 electrons all going to burst out. Okay, so let's say I got now for my zinc here. Let's say this is zinc now. Zinc. Okay, right. And I draw here like that. Okay, so to give you a better picture, I do this so I thought you can use it better, but now mine. Okay, this is all zinc. All right. Remember the solution here. To make it standard, I put 1 molar of zinc. Concentration of zinc Zn2 plus here is 1.00 mole per dm cube. Okay, so this is the standardized. Well, this is standard. They say under the standard conditions. All right. So zinc will throw out. Okay, and will become here will be Zn2 plus Okay, Zn2 plus, Zn2 plus. Okay, all will be here, be a double electric layer again. All right, so all this will come out. Okay. All right, so is Zn2 plus here, Zn2 plus here, also here, this plus, okay? So they form a double electric here, okay? And on surface here, 4 electrons, thousands of them. Let's say here we got, let's say about 1,000 million, whatever. Okay, let's represent by 100, okay? So for hydrogen is 50 electrons. Let's say it's 100 electrons, okay? Here on the surface is 100 electrons. That's not in equilibrium, okay? This way, so now is the equilibrium of Zn solid plus AQ give you Zn2 plus equals plus 2E, okay? All right, so this is the equilibrium. And let's say copper now. Here, now it's copper. Same thing. I put copper. Copper is great. You know it's very unreactive now, right? It still can throw out electrons, okay? It still can, but less lah. Okay, here, okay. So again, you form a double electric layer. Okay, this copper metal here. So after throwing out, I'm going to put again. Okay, okay. Remember this solution here. Make it standardized. I put here copper 2 plus concentration. Okay, equals to 1.00 mole per dm cube also. Or everything is standardized. Okay, so you form copper 2 plus here. Cu2 plus here. All along here, you form another double electric layer. Okay, so at temperature 25 degrees centigrade and temperature equals 1 atmosphere, you will get another double layer. But of course, here we have less electrons, you know. Okay, less electrons. Let's say here is 25 electrons or 25 million or whatever. Let's put it 25. Okay, right? So electrons here. Okay, so now I've got 3 systems. Okay, they are metal and gas. Hydrogen is what we call use as a standard. Okay, so what we do is we want to build up, as you see in your, well, I didn't put it down here, but it's here. Okay, see, you'll be given your data booklet, and this is what you will see. What they call standard electrode potentials, and you must know how to use this well. Otherwise, you cannot solve it here. Right now, see. Standard electrode potential, SEP, to have a short form, it's called SEP, standard electrode potential, okay? Right? As contrary to SCP, standard cell potential. After you see the difference, okay? So they are called standard. Why standard? It's not here, why? See, standard. What's temperature at 25? And the solution for all these things here is 1 mole per dm cube. 1 mole. Everything is 1 mole. Okay. So that's why they put a standard. Okay. So this is called a standard potential readings. And this in exams, you'll be given all this. How they derive this on here? Okay, so I'm going to show you how they derive this thing called the standard potential. How they get this value? Huh? This value, how do you get this? Chlorine here. Okay, now you see that here. There are 3 types of systems. One, of course, remember, is always going to compare with hydrogen gas or the hydrogen standard hydroelectrode. Okay, so there's 2 systems here, or 3 systems here. See, copper, metal, and your solution. Okay, metal and your solution. Can be iron 2 plus, iron 3 plus. Can be also ions and ions. Okay. Can be also gas and ions, chlorine, gas and ions. So we look at all these 3 systems, okay, one by one. Don't worry, I'll go through all this with you. All right. So here, let's go back to here. So the 2, this is the metal system. Metals is easy to deal with, can understand easier. So what happens is now I want to compare. Okay, I want to remember, see, can I measure this potential of 100 here or 25 here, or hydrogen here is how much here? Hydrogen here is, I didn't put down here, I put the other one. Too bad for me. 50 here. How can I measure them? You do by a difference. Okay, so now what we do is we're going to hook them up like this. Okay, here. Now let's say I put now here. Okay, I'm going to compare. This is called my test electrode. Test electrode. Okay, in example, it's called a test electrode. Now here I want to use zinc and zinc 2 plus. Okay, so I put zinc here, metal, solid, and here my solution of Zn 2 plus of what is this? 1.00 mole per dm cube, right? Because this I would then will get a standard. Okay, now here to make it standard, I will remember this like DP rocket. Okay, now here is a platinum, must say platinum. Okay, so put PT with it, don't need to put platinum, doesn't matter. Salt bridge. Salt bridge is to connect, to cause the ions to flow, to connect. It's called to complete the circuit. Okay, in form 5, we say complete the circuit. Okay, so now this is immersed inside here. Okay, so I pass in the gas I want to is hydrogen gas, and the pressure is 1 atmosphere, quite a strong pressure. Bam, inside, no air inside here, guys, no air, nothing here except hydrogen gas. Okay, and temperature all 25. Now this is 1 mark, no. Okay, all right. So now remember, electrons flow from higher electron density to low electron density. Now, zinc, of course, will ionize more. You know, here I told you there is 100 million, or let's say 100 electrons. Here at equilibrium is 50. Right? So they all want to come out. Electrons are going to flow. Guess who? Now, this is the voltmeter. Okay, voltmeter. So both are going to come out. So guess who is going to overcome who? Obviously the 100. Okay. So it will flow and will beat this fellow here. So 50 is against it. So overall movement is how much? It will be 100 minus 50. So the overall is 50 electrons are moving here. That means your zinc will be negative. Here will be positive. How do you know? You know it from the voltmeter here. See, in experiment, you put the negative onto the positive pole here, right? It will give you it will deflect by is below 0.1. Okay, the voltmeter must give a reading. Okay, give you a number reading, a numerical reading. Okay, otherwise that means you have the wrong poles. So it will give you a reading here, and that means this is the negative pole. Electrons are going here. So this is the flow of electrons. That means what? Zinc has a higher potential, higher electron potential or electric potential than who? Than the potential. T-I-R, my spelling. Okay, than hydrogen. Okay, so hydrogen is positive. That means it will receive electrons. Now remember, now here is where the whole thing is. So what? So this is the whole thing you will get inside an experiment, right? Once you hook this thing up, you get a measurement here, the voltage here. Now, let me tell you what the voltage is, because actually you can get it from the table here, right? See the zinc. This is the value. Yeah. Now take the magnitude for 0.76 means what? Means the reading here is 0.76. There is no positive or negative one, right? The only thing that you've seen that here is negative pole. Remember, there is a red and a black pole in your voltmeter. Have you seen before? Well, I'll show you. Okay, I'll show you here. If you want to see, okay, voltmeter. I hope you can see it. Voltmeter. Voltmeter first. Voltmeter. Okay, I search for you and you can see voltmeter. Okay. Stop sharing screen. I should share screen. Okay, see that? Okay, right? So there's a red button and a black button. Yeah, okay, right? So red means positive, black means negative. Okay, so if you connect it correctly, right, they give a reading. Bam, give a reading 0.7. Okay, right? So, okay, stop sharing screen. Let's go back to that part there. I don't want to see my face now. Okay, here. Okay, right. So remember, red means positive, black means negative. Okay, so you can see the right reading here. Okay, so now, so you can see here, in here you get, this is the size of the potential. Okay, the negative means here are the poles occupied by zinc. In comparison, what? The hydrogen. That means zinc is more electronegative than hydrogen. That's why in the form 5, zinc is more reactive, isn't it? Okay, so that's the reason why here. Now let's go to here. Okay, so because it's 50 here, this 50 is a exaggerated one. Now we want to see what actually happens here. Okay, what are the reactions here? Ionic reactions here. This is very important. Remember, inside here there is an equilibrium of H2 gas plus AQ reversible to give what? 2H plus equals plus 2 electron. Okay, they are reversible. They can go forward, backward. Because inside here, there are two systems. There are two H2 from here, and H plus from your H2 from your 1 molar of HCl. See, there are two systems. They can go forward, backward, depending on where they push it. Same thing here. There are two systems, zinc from the metal and zinc 2 plus from this solution here. Right? So here you have also, I put down here, Zn solid plus equals to give you Zn 2 plus equals plus 2 electrons. I put down here so can compare them, okay? That's electrodes here. So it's H2 gas plus AQ reversible 2H plus 2E. So now, so is it going forward or backwards? Is it going forward or backwards? Okay, when you put the system on, when you close the key, when you connect the circuit. Okay, now from here you can see from experience, well, electrons are flowing from zinc to here. Okay, we'll put a blue color to get can see better. From here. Okay, electrons are flowing from here. That means zinc here is underway oxidation, right? It's going to go continue until doomsday, kind of thing, until the whole thing rot, until zinc no more, right? Because it's high potential, it will keep on going. As it keep on going, which means the forward reaction is happening now. Because this electrons is coming out, right? And going to hydrogen. See? So that means that what is happening here is because, how do we know it's happening? Because it's negative. Negative pole means what? Source of electron. So electrons coming out here, okay, which means it came out from where? From the zinc, which means here I cannot put two ways anymore. I put there. So what's happening is zinc solid, sorry, Zn, not Zoro, plus AQ. One direction now. Use zinc 2 plus equals plus 2 electron. Yes. So if electrons are coming here, pom, 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 ting, 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 and on the surface of this thing, of this platinum here is full electrons now, right? So if you look at this part here, if it's full electrons here, right, if this increases a lot, what happens? You go backwards in. See? So what's happening here is actually the H plus from here, the H plus, the 2H plus, right, will have to equals, will have to undergo reduction to give you H2 gas. That means more H2 gas are being produced here, okay? So this reduction, okay, a positive pole, right? This is a positive pole. This is your negative pole. So undergo reduction here. Why? Why? Because it accepts electrons. Here undergoes oxidation. Why? Because it donates electrons. Okay. So now you got two systems going on. So as long as you keep the key closed, right? The electrons flow here. These are the two equations. Okay. So the overall equation, you just add them up now. Okay. So what's the overall equation? I'm going to put it here. Okay. Right. So here is one here. So you put H, 2H plus. Okay. Equals, right? Plus 2E. to go to H2 gas. So you O all the filler, right? So you got zinc solid. It's called overall equation. Overall equation. These are called half ionic equation. Half ionic equation. Okay. So you can see, right? Overall equation. So B is N plus 2H plus. Okay. This got cancels off. N plus AQ goes to Zn 2 plus aqueous plus H2 gas. Okay. Now, there's a way to write this equation here, which means there's called an IUPAC system. I'm going to bring you to here. It's not required now, but just in case you want to know, okay, it's no big deal. Like here, called a cell diagram, okay? Right? Now, all the things are here, is in notes here. You can see there, I just want to use it to draw. Right? Now here. I thought I did it. Never mind, here we go. All right, zinc. Sorry, I thought I did zinc. Okay, here. Now, right, see? Right, so now this is the overall. Okay, now this zinc, this is oxidation. Negative electrode is it? Okay, oxidation. Right, this is your reduction. This is a hydrogen electrode. These are your ionic, you got half ionic equation. Okay, right? This is your full equation, not FOOL, full. Full or overall equation. Okay. So now this is called a cell diagram. If you want to know, fine. You don't know, forget it. Okay. Now in the IUPAC system here, for SEP, for standard electrode potential, that means you must have hydrogen. Must have hydrogen. Okay. Right. For SEP, no hydrogen, but I explain afterwards. Again. So for SEP, hydrogen will always be on the left hand side. Left hand side. My left hand now. Okay. I'm facing the thing. This is the right hand side. Here must always be hydrogen. Okay. Right. Okay. And it always will be negative 4. Okay. I think I may make, yeah, now I'll come back to this later. I should have done this. My copper is the other side. Never mind. All right, let's do copper first. Okay. Actually, now I go on. Okay. See here, according to IUPAC here, whether hydrogen is negative or positive, it doesn't matter. Right? In the IUPAC here, hydrogen left side must always be negative. Okay, negative. Right? So to be negative, that means it must be undergoing reduction. Right? Means don't electrons in, right? Even though it does not happen, you put it down. I think I better don't do this, but okay, I do the copper first. I know you'll get confused. I was stupid. I should have said I put copper here first. Okay, now my copper first. Copper first. Okay, copper first. Easier. Let's go to copper here. Now, if it's copper, simple, right? See, I thought I planned, but I didn't plan properly. Now, copper is going to again, cause a double electrode here. Come on here. Okay, so you get copper, just like the zinc here. Okay, it will come up and form copper. Say here, come up. Okay, here's copper 2 plus solution here. Copper 2 plus. Okay, of course there's copper. There is copper 2 plus there. So the amount come out is less now. Copper 2 plus. Okay, copper 2 plus, and with all negative electrons here. Okay, so I told you that here, well, there's only 25, very small amount of electrons coming out. And here hydrogen, okay, hydrogen will come out here. So be here, H plus 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 here. And this is a lot of electrons here, right? And I told you that, well, hydrogen comes out is about 50. So there's 50 electrons here. Guess now who is got a higher potential? Of course, hydrogen, right? 50 goes here, 25 goes here. Oh, so it's a win. So here goes over here. So the overall will be 25 electrons showing here and from here. So hydrogen now is negative. I said just now, sorry. That's why I say that zinc is negative, so now hydrogen is negative. This is very important, okay? So it's negative here. So it's like this is a better example, okay? So it's negative here, right? So remember, I've got my earlier equation here, H2 gas plus EQ, reversible give you 2H plus gas equals here plus 2 electrons. Here, of course, copper solid plus AQ, reversible copper 2 plus AQ plus, okay. So we say that, well, here got 50 electrons, okay, at equilibrium, this got 25. Okay, so when you put them together, when you put on the switch, right, there's going to be a reading. You put wrongly, I mean, this will be negative pole here, negative, okay? The red color will be here, okay? You put the red on this side, I cannot. It will give you a non-reading. So, all right, so in fact, this one here, as you see here, what is the reading here? Okay, if you look at the electric potential here, this is the reading you get. All right, let me show you. Copper, copper, copper. See you. Okay, here. Copper 2 plus and copper. 1 plus different, no, 1 plus different. So it's 0. See, 3034 is a reading, and positive will be the pole of the copper. Okay, so the pole of the copper is positive. That means here is positive, correct? Okay, because right, it's receiving electrons. Okay, positive is receiving electrons. So hydrogen is electron donor now. Okay, so the value here is 0.34. They would have positive, negative, the positive because this is the positive pole as well. Okay, so why? Because zinc, your hydrogen here is has more electrons. So if that's the case here, right? If that's the case here, that means for this negative pole, okay. So what is happening? What is the half ion equation? Of course, hydrogen must be coming out, okay, to supply the electrons to copper. See, so the half ion equation here. Half ion equation, okay, will be H2 gas plus aqueous to give one directional, give 2H plus aqueous plus 2 electrons. And over this side is a positive pole, right? To receive electrons, it must be going this way, is it? It's not. Copper must be depositing on here. So half ion equation is copper 2 plus AQ plus 2 electrons. Whose electrons is this? Hydrogen electrons to become one arrow, one directional copper solid. Okay, right? So this is now oxidation. This now reduction. Okay. Now the overall equation you can put either way. You can put, let's say I put over here. Okay, Cu2 plus equals plus 2 electrons will give you copper solid. Okay, so the overall equation would be, you cancel off the electrons here. Cu2 plus aqueous plus H2 gas plus EQ will give you 2H plus aqueous plus copper solid. Now this is the overall equation. They will ask you what? Overall equation. They also ask you now this is called the standard electric potential here. What's the value? Now the value is 0.34 volts. But the sign here, right, has two meanings. One, first of all, it will be the sign, right? It will be the sign for not hydrogen, but for the copper, the positive. Okay, so it will be the sign for the metal, because the other side must always be hydrogen one. Okay, for the standard for SEP. Okay, SEP, standard electric potential. Okay, you must compare the test electrode with a hydrogen standard electrode. Must always be one. So this is the sign for the metal electrode. Whatever metal electrode is, okay, or whatever non-metal electrode, or whatever gas is. The left-hand side, okay, see here, okay, now, so for the cell diagram, okay, we call it a cell diagram or cell abbreviation diagram, okay, that's what I'm going to go through. Now, don't have to care about this. Now, this is the way I call the salt bridge here, Now here is negative, always negative, this is always positive one. Okay, so this is how it goes. This is IUPAC system. IUPAC system. And here, negative means that it must always be what? Oxidation. Right? Because electrons coming out. Okay, here is always reduction. Because why? It's going to accept electrons. It's always going to be donate electrons. Whether or not it happens or not, doesn't matter. And IUPAC system say here must always be hydrogen. Okay. So now, by chance or by itself, hydrogen is negative one. Yeah. Okay. So it's easier. So I say I should deal with this first. Okay. Hydrogen negative. Okay. Got more electrons here. Okay. Right. More electrons here. I play the game for you lah. I say it's true lah. But actually, you can find it out. How do you know it's negative? You do an experiment. An experiment they prove it's actually negative. Copper is positive. That's how you know. Okay. So I tell you ahead of time that it's negative. You ask me how is it negative? Well, I did experiment. I trust Mr. Light. Right. So negative. So negative. So okay. So if it's negative, that means this is happening. Right. This is happening. This is happening. How to write it? Very simple. That means it will undergo oxidation. So I write here. All right. Now here I'm not put a straight line. This represents the platinum electrode. H2 gas becoming H plus. Okay. Now sometimes they put the platinum down there. Okay. Now let me show you here. I hope I don't get it wrong. That's all. Yeah. You can see. Okay. So now they put platinum first. Platinum slash. Okay. The slash means that there's a change of state. H2 becomes, this is what? Oxidation. And this is actually happening. Okay, this is actually happening. Sorry, here. Copper first, sorry. I mixed up here. Copper. Okay, copper here. Okay, see, hydrogen is always on the left-hand side one. Left-hand side. Okay, this is always, what? It's always oxidation. Okay, put a slash here to show you there's a change of state, solid, okay, platinum. And of course, here is going from here to here. Which is true, isn't it? Right? For copper, isn't it? Hydrogen becomes H plus. And the double line here represents the south bridge. Okay? So here, of course, is reduction. Copper 2 plus going to copper now. Yeah. Okay? Yeah, going here. So now this going through. And of course, now this is called this SEP, standard electrode potential. Why? Why electrode potential? Because I'm comparing copper of copper. This is of copper. I'm comparing what? With hydrogen. And it's positive 0.34. Positive, why? Because copper is in the positive electrode. Okay? Hydrogen is negative electrode. And so this represents the poles of the test electrode. Okay, electrode. Because the other electrode must always be hydrogen. Always. For standard electrode potential. Okay, now. Okay? So positive. Second one, the positive means positive also means energetically feasible. Energetically what? Feasible. What is feasible? It means this reaction. This reduction. It means copper 2 plus go to copper will happen. It will happen. When you compare with hydrogen, it will happen. That means feasible. If it's negative, it means that it won't happen. It means the reverse will happen. Okay, now hold on the thought now. Let's see here first. Now for zinc. I thought for zinc just now I jumped the gun, right? Remember zinc, what zinc happened was zinc undergoes oxidation, right? Because zinc is more powerful. There's 100 electrons here. Okay, hydrogen only got 50. Yeah. So zinc actually this will happen. Zinc will dissolve, it becomes N2 plus, and hydrogen H plus will become hydrogen gas. So this is actually what's happening when you connect the cell. Zinc dissolves, okay, H plus become H2. But when you write the cell program, you cannot write like that because IUPAC system says that you must write left-hand side must put hydrogen electrode, right? And you must put as if it's negative. That means it must undergo oxidation. But here to here undergoes what? Reduction. I don't know. So you must write as if it means not true. Okay, you write something is not true. Never mind. There's a reason for it. So write something not true, which means you write reverse from here to here. Okay, H2 becomes H plus, right? And of course, if this oxidation, this just this much reduction at Zn2 plus become, of course, not true, isn't it? Because it happened the other way, but right this way. So you put the E0 values as this value is correct, okay, from the voltmeter. The negative here, negative is what? Means two things. Two things. First, it will mean that your zinc, your test electrode here, okay, is negative, which is true. Secondly, it means it will not happen. This will not happen. This your reduction will not happen. It will happen the other way, which is true. You know? So two things it will tell you inside. Huh? So when you write this part here, this part here is written in the reduction. Now, Zn2 plus becomes the N, right? Copper also same. See? Copper 2 plus. Compared to hydrogen, they're always in reduction. That's why the table here is all reductions, you know. See? Reduction. See? They're all reduction one. That's why reduction? Because you compare with hydrogen. So it is very beautifully done, even though it sounds quite weird. Don't happen how I write it. It don't happen like here negative means it won't happen. It will happen the other way. Okay, so all this is called standard electrode potential because all these half cells here, they call half cells because two cells, one must be hydrogen, the other is a test electrode. All these are called test electrodes. Okay, so when all these systems here, all these electrodes here, this how electrode compared to hydrogen, right? And under standard conditions here, they will give these readings. They will give one. This is a recording of all the experiments done with like silver here. I put silver electrode here, and this silver, and I put silver ions here, Ag plus, 1 molar, and I connect it to hydrogen, the standard hydrogen electrode, SHE. The voltage here is 0.80, and I know that here is be positive and hydrogen negative because here. And I know that if it's positive, that means this will happen. That means this fluid will undergo reduction. That means this is going to happen. See now. So from here, again, let's say I put aluminium. This one here. I put aluminium here. Okay. This half cell. Put aluminium here. And the solution of Al3 plus here. Okay. Al3 plus here. And it's 1 molar. Why? Standard. Okay. E standard. Okay. And I connect to SHE, standard hydrogen electrode here. Okay. And guess what's the reading here? This one here. 1.66. Negative means what? This is going to be negative pole, aluminium. That means this one's going to come out here. Right? So that means that it won't be this way happening, it will be this way, which is true. It will just reverse. So the negative sign, this one tells me everything I need to know. Compared to what? Hydrogen electrode. Beautiful, isn't it? You understand or not? Think of what to think, okay? That's why I say that all these systems here, right? All this is called standard electrode potential. Because the test electrode, all these are test electrode. They're called test electrode. Compared to what? Compared to SHE, standard what? Hydrogen electrode. That's why you look at the marking scheme. I show you the marking scheme for the question so you can see the question. Okay, the two difference or standard potential was that standard potential is 76. Okay, look at page 76. 76. Okay, the question. I give two marking scheme. See, what do you understand by the term standard electrode potential? All right, yeah, okay, standard electrode potential. See, electrode potential or SEP. Okay, now I'll show you the other one first. Okay, this SEP, the other one is standard cell potential, which is 118. I'll show you that they're different. Okay, now here, see, they ask you, I say here. Okay, now standard cell potential. Let's put a cell here. Cell potential, SEP. What's the difference? Now, I'll show you the marking scheme. Okay, the first one here. I got two marking schemes, so you will be very sure. See the EMF, right? EMF means what? The voltage, okay? The EMF. I say EMF. This is the voltage. Okay, this is the voltage. Voltage. Where do you measure the voltage? The voltmeter lah. No, when you connect it, no. Voltage of a cell made of a test electrode. Here, this one means that all the electrodes that you use in here, every electrode you use in here. Okay, let me show you again. It's quite interesting. I mean, the thing is, how these things didn't develop, So if I don't teach you that one, I don't understand what it is. I just use it like blind cows, Yeah, all these systems here are called test electrodes. This is the one part of the cell. See, this part of the cell, and this part is what cell? For SEP, is your hydrogen electrode. Has to be the rocket here, DAP here, H2 gas, and here of course is a what? H plus, and 1 molar. Okay, temperature equals to 25, pressure 1 atmosphere, and here this part, okay, now the voltage here, and this is a cell salt bridge. Here, I just finished with your metals now, okay? This part is a test electrode. All these things here, okay? And the voltage, this is the voltage here, under standard conditions, okay? The sign here represents the poles here, positive or negative. Negative means it will go backwards. Positive means it will go forward. So the sign here can tell you two things. One, of course, the poles. One is whether the forward direction can occur or not. So that's why it's called standard potential. So this is called, all these things here. Now, of course, they put also hydrogen here. See, hydrogen is, what is hydrogen? Zeros, That's why it's a reference. 0. So compared to hydrogen, everything here, right, is either positive or negative. I said, no. So that's why the IUPAC system is very beautifully done. The fellow thought is a genius. You ask, why you do all these things? Because you do all this, even though it doesn't occur, you put occur is for the system here. So now you can predict anything, under the sun, any test system. So let's go back here, okay? So remember that it's the EMF or the voltage of a cell made out of a test electrode and what? The one way, standard hydrogen electrode. So you must have this there for you to get a mark for SEP. Let's look at the question again. All right, questions in page blah blah blah, page 76. Got two. I showed that one on 83. The other one is 83. There are a few of them. So standard electrode, not cell potential. 2 marks, man. Why 2 marks? Now I'll give you the other. This is 050. Okay. I'll give you the other one. See. Again, same. The EMF of a cell. EMF of a cell. I say, come on, baby. EMF of a cell. Learn by heart, okay? Of a test electrode. And what compared to a standard hydrogen electrode, SHE. Okay, or the EMF of an electrode compared to SHE. You can put SHE here. Standard is called standard what? Standard hydrogen electrode. Then you must put the conditions of the standard electrode potential. Temperature equals to what? 25, okay, not 0, okay? 25 degrees centigrade. Or this one, Kelvin. And 3 things, no? All right. Pressure equals to 1 atmosphere, and the concentration of ions, concentration of ions. I forgot to tell you, but must say 1 molar. 3 things: temperature, pressure, and concentration. Actually got one more. No, that means if it is a solution or gas, you must have platinum as an electrode. Okay, later I didn't go there. Is that clear? Right? I've taught you how to derive the SHE. Right? Now I'm going to go to 2 more systems before I got 10 more minutes. I know I'm going to show you now for a gaseous system and which has no metals, and one is for ions and ion system. Okay, are you with me? So now you know, So go back and go over this one and see how we understand. Now, see here, I want to show you the syllabus first, all right? So I've gone through with you to tell you how we found the standard electrode potential, right? Represented by E naught, that's all. For standard cell potential is represented by E naught and the cell here. That's the difference. This one here must have SHE. So no need. No need. Later you can make anything, any half cell, like what you did in your Daniel cell, blah, blah, blah. Okay, now, right? So you see, the cell is called redox. That's why you can see this is called a reduction potential. You look at some books, this part here. This part here, right? This is called a reduction potential. See, or okay, this is called a reduction potential. Why reduction? Because it's reduction, right? Because it's always in the positive part, isn't it? Right? Okay, right? Okay, right? Okay, because it always receive electrons, right? It has to. Okay, so think about it. Okay, now let's go back to here. All right. So now here you can see I finished the first part here. Right? Describe standard hydrogen electrode is SHE. Methods to measure standard electrode potentials are metals. I've done metals already. Now we talk non-metals. Okay, with the ions. Okay, right. Metals with the ions. Now we talk about non-metals with the ions. Okay, and lastly, ions of the same element with different oxidation state. For example, Fe2 plus and Fe3 plus. Oh, there's no metal where electrons travel. Or MnO4 minus and Mn2 plus. As long as the redox, you can read it. As long as electrons are being transferred, you can measure. So we're going to look at these two things now, okay? With the time permitting, I'm going to go on now here. All right, now here, as I said, nice website which I got. So now is, first of all, metal and metal ions. See, if it's Fe and Fe2 plus, can be Fe and Fe3 plus, no? See, they're both different. Look at it for a while. Look at it for a while. So depending on what system you have. I ain't got a few, no? Okay, here. Right? Four systems. Fe and Fe2 plus, which means for this case here, right? I got my hydrogen electrode here, SHE here. Here is the salt bridge. If it is this one here, I got iron, metal here, solid. Here is your Fe2 plus. Fe2 plus, concentration is what? 1.00 mole per dm cube. Yeah, and of course, the potential here, blah, blah, blah. The voltage here is how much? 0.44. Here negative, and here's positive. Okay, if I got this system here, what does it mean? Which means, again, this is my hydrogen electrode, okay? And here's my test electrode, iron here, metal. Here is my what? Here's a salt bridge. Here's what? Here's concentration of Fe3 plus, iron chloride 3, 1.00 mole per dm cube. Connected to the voltmeter here. And here the reading is 0.04, see now, smaller. And what is the charge here? Also negative here. Now this one here. Of course, I got iron metal here for electrons to reside. No, electrons can electron can stick onto the metal. I don't know. But here, they are no metal. They are both ions. 2.3 plus here. So what do I do? So this is what they suggest here. So here is this system here, right? So here I must have both of them, Fe2 plus, I put both, it's equal to 1.00 moles per dm cube. And also mixed together with another the iron 2 chloride and iron 3 chloride. Okay, also 1.0 must follow the standard procedure. Okay, and platinum here. Platinum is neutral. Same thing now. I connect it to my hydrogen voltmeter here to here. Okay, I put a salt bridge here, right? Then I measure. Okay, now of course here there will be a transfer here. Of course, now what actually happens? Let's see. Okay, see, plus 0.77. Okay, plus 0.77. Okay, right? Now I'm going to do here. So I found that from my data, right? Remember reduction, right? Remember Fe, right? 3 plus. That's what they wrote there. No, plus. I show you again. Okay, reversible. Very important. Okay, equals here. The E thing here is equals to plus 0.77. Now, see where I'm correct now. 3 plus first. See, 3 plus. See, 2 plus. That means 4 is what? Is reduction here. Reduction. That's why it's called reduction potential. Okay. So it's positive here. All right. I just repeat it here. Right. So now if I put like this here, right now, can you tell me? Can you tell me? Right. From theory wise, because I didn't do the experiment. Okay. What will be the reading here? What's the reading? Okay, I can hear you louder. What? Okay, of course, 0.77 volts. It's not. Because everything is standardized. Here's got a 1.00 mole per dm cube of H plus. This is, of course, temperature goes to 25 degrees centigrade, pressure to 1 atmosphere. All these are standard now. Yeah, so the salt bridge here. Now, which is positive, which is negative? Can I know? No, I didn't do experiment. All I got in an exam is this value here. Will this determine anything? Of course it will. I told you the positive sign means what? Means the test electrode is what charge? Positive charge. This is negative charge. Correct? That means, once I know this, can I find out what are my ionic equation or not? And then my O equation or not? I can. Why? Because negative charge means this is a source of electrons. I'm going to put a red color here now. See, very important thing. It's fantastic. This whole thing will give you now. So this is a flow electrons. Going here. Whose electrons are this? Hydrogen. Now remember here, all they give you is the reduction potential, right? H2 gas plus equals give you reversible 2H plus equals plus 2E. Where I get this equation from? Again, the table. This one here. Oh, sorry. They give it in reduction form. So I'm wrong here. So let's see, can I simply write? No, I purposely it's like trying to fool your leg. Okay, remember this is what you get from the thing. So now remember now. Look again. It's written in reduction 2H plus. Okay. Yes, 2H plus. I'm putting out 2H plus. Good night. 2H plus equals plus 2E. Remember, I write all these things that is from the table. So the table is very important. Yes, not. Now I got this and this from a table. These two are from tables, and this way is what? Both are reduction. Because they accept electrons now. Okay. Yes. Okay. Now, therefore, which is the actual equation that's happening? Which is the ionic equation that's happening for hydrogen? Remember, in reality, from experiment, this is negative pole. Negative. Why negative? Because, right, the electric potential, the SEP for Fe2 plus Fe3 plus is positive. 0.77. This value tells you the reading. The positive sign tells you what? The iron plus is positive, isn't it? So this cannot be positive. It's not iron, it must be negative, isn't it? Right? It has to be. So it's negative means what? Electrons are coming out. Right? Going out here. If electrons are coming out, that means it must be going where? Forward or backwards. Forward, it must accept electrons. Backward is donating on. Right? So it must be over here. What's happening here? Is H2 gas becoming, or plus equals, I put, okay, becoming what? 2H plus equals plus 2 electrons. This is the electrons that are flowing out here. I don't know. Yeah. And so what's happening here? Huh? Fe2 must become Fe3 plus, Fe3 plus, Fe2 plus. Because it's positive, it means that it must be this way is correct. Which means here, the Fe3 plus equals is accepting electron to become one directional Fe2 plus. Positive, that means it can occur. Okay, so this is in the positive pole, this is the negative pole. Okay, now put down here, right? Watch out. So H2 gas plus AQ give you 2H plus gas equals 0. Okay, now the overall equation, okay, take 2 electrons, right? Sorry. So times 2, 2, 2, 2. So the overall redox reaction, that's why it's a reduction, okay, be H2 gas plus 2 Fe3 plus equals, well, cancels one, yeah. You can put plus equals additional equals plus all equals here. Go to 2H plus equals plus 2 Fe2 plus equals. Now this is called the overall equation. See? So beautiful. All you can get because of this value here. Plus 0.7. And where do you get this value from? Where? In the exams, where do you get this value from? You go to the lab and do experiment. Idiot. From the data booklet. Here. Beautiful, isn't it? Beautiful. Yes. Wonderful. Okay. Now the last one. What happens if it's a gas? I put down here, it's for gas. See, I land my work. So if both gas, like here, chlorine, okay, now let's do this here. It's chlorine here. All right, chlorine here. Okay. This slide, don't play, I tell you. Okay. Up here. All right, last one now, then we finish. Okay. I know I keep it too long. I don't know how many use my videos to waste my time with this. Okay, see chlorine here. Okay, right. Okay, so because this is S standard electric potential, that means my test electrode is my chlorine. So if it's a gas, right, I must use platinum as my thing here. So see, platinum, this platinum. Chlorine gas pass out here, pressure 1 atmosphere, the H plus here is equals to, we don't care about 1.0, okay. First, chlorine here must be Cl minus here. Right? It's also 1.00 mole per dm cube. Quickly, okay? Time is up. So here's chlorine gas, Cl2 gas, and pressure on. Okay? Blah, blah, blah. Temperature is how much? 95. Okay? Now this see, okay. Don't care all this now, okay? This is a nice diagram. I just cut and paste. So this is hydrogen gas. This is your standard hydrogen electrode. Okay? As you see. Right? 1 molar of H plus. Beautifully done. So now they ask you actually here. The question actually ask you later. I'll show you the question. Okay. Now here. So all you have is your data booklet, which is on here. Cl2 plus 2E blah blah give plus 1.36. Okay. Cl2, all you got here is Cl2 gas. Okay. Plus 2 electrons. Give you 2 Cl minus equals because reduction, okay? Plus what is it again? Let me see. How much is 1.36 now? See, plus 1.36, okay? 2 Cl minus, okay? Right. 1.36 plus 1.36 volts. Now, this is your what? Standard electrode potential. This is your test electrode. So, can I find, first of all, which is my positive pole, my negative pole? I can. From where? From the sign here. So, the sign tells me the test electrode here is positive pole. So it's positive pole. It's negative. I don't need to go to the experiment and do the experiment. They already done for you already, idiot. Okay. So if that's the case here, which is the flow electrons? That's right. Negative pole to positive. Okay. And what's the value here? 1.36. Very high voltage. Okay. So can you tell me what? Because remember, inside here, there are 2 systems here. It's H2, right? Gas plus 2 electrons becoming reversible, isn't it? 2H plus equals. Here is what? Here is this one here. because there are two systems here, this one here. So who is becoming who? Which one becoming which one is becoming reduction, which one becoming oxidation? Can you know that? Of course you can, because electrons coming from here. That means it's going to be forever. That means it's the source electrons here. That means here is undergoing what? Here undergoing oxidation. So which part of oxidation? Forward or backwards oxidation. Okay? Oh yeah, this is something wrong. Why didn't you tell me? Sorry about this. I said, how can? Now mind, Mr. Let make mistakes. Right? It's H2, isn't it? Right? H2. H2 gas to H. No. To H plus. Ayo. See, when you hurry, I'm watching the clock, the stupid clock. Time already, I know. Okay? It means reduction, okay, H plus here, becoming H2 gas here. Now look at this here. You got a problem check here. Right? See, hydrogen. Right now. Reduction here. Yeah. Okay, 2H plus, okay. Now mine, I'm going a bit more. Okay. So which means that if it's going to be oxidation, it means it's going this way now. Right? This way here. Electrons. So here you put, well, for what pole? For the negative pole. Negative pole is going to be H2 gas becoming what? 2H plus equals plus what? 2 electrons. No. And for the positive pole, it's going to go in what? Reductions in. Which means that Cl, right? Cl2 gas plus 2 electrons to give you 2 Cl minus again. Okay? So time. So right now, it's like it's received electrons now. Okay? Electrons, it means undergoing reduction. Reduction, it means this correct. Positive means it will go forward here. So times here 2 or ngam. So great. So get right now. Let's check first, man. Okay, 2, okay, right? Okay, so get H2 gas plus here cancel off, right? Cl2 gas goes to 2H plus gas plus 2Cl minus. This is a overall equation equals. It's a redox. Is that clear? Okay, so this is the overall reaction, and this is a half ionic equation. Half ionic equation. And that's how you treat 3 types of electric potentials. Metal and metal ions right here. Okay, metal and metal ions, right? Gas and ions, ions and ions. Okay, so there are 3 types of situation you can see, right? And here represents all the 3 types. Okay, think over. I think this is a very important chapter you will use in your physical chemistry, your inorganic chemistry. Okay, well, sometimes they use in your organic chemistry. Okay, so goodbye and see you again. Okay.